Welcome to Water Pressure and Flow. Now, how water pressure and flow impacts the operator. Low flow and sudden pressure drops can cause low water error indicators on combi and steam cooking equipment and coffee equipment. But it also has a profound effect on fountain dispensing, on its Brix ratio, the ratio of water to syrup, and the quality of that beverage being dispensed to the cup. You've all had that experience of someone flushing a toilet in a building while you're taking a shower and you suddenly get hit with hot water. That's not because the hot water is getting hotter. That's because the pressure has dropped in the rest of the system on the cold water side. That it's dropped that flow throughout the building. So you get a shot of hot water. Well, the impact of that in food service applications is when something else demands water, part of that flow is taken away. So in the case of a fountain dispenser, what's going to happen is you're going to end up putting more syrup in that cup than you would normally have, lowering its profitability and impacting the mix of that product and its flavor. And since fountain dispensers tend to be the most profitable items sold in food service applications, the change in that Brix ratio directly impacts the profitability of that system. And in steam and combi and oven applications, those low water errors may require a technician to come out and reset that system, driving nuisance service calls and expense. And in coffee, that low pressure and flow may not trigger a low water error, but what it's going to do is cause short fills of those pots and dispensers, impacting profitability by not brewing a full cup of coffee or slowing down the rate at which they're producing coffee, so they're not turning over that product as quickly as they should, may cause their customers to wait longer than they would normally like. And its impact on filtration can be significant because pressure is the driving force that pushes water through a filter. It's what helps strain the debris out of the filter. But as that filter fills up with debris and we don't have enough force to push through that built-up dirt load, what happens is we lose some of the capacity of that carbon filtration behind it, not getting maximum yield out of our investment in that filtration system. So in flow, water and pressure and flow have significant impact on all applications in food service. In a typical food service operation, you have city water and a water softener, and that could be feeding a reverse osmosis system, the dish equipment. The reverse osmosis could be, servicing all the coffee, tea, and espresso. And then you have the untreated water going to the bathrooms, the fire alarms, toilets, and sinks. And then you have point-of-use filtration that might be going to the beverage and ice. So what happens when water in one of these areas demands water? What happens to the rest of it? Well, that can create a chain effect through the entire system, dropping pressure in all the other applications, impacting their function. So sources of low water pressure or poor water pressure and flow in a building. Well, you can have just low water pressure to the building. Chicago is notorious for having low water pressure in buildings down around the 20s, and quite often there are booster pumps in the buildings to boost the pressure. The other thing just maybe undersized plumbing. Poorly designed plumbing inside the building can lead to restrictions in that flow. So a 3/4 inch line can carry more than double the water than a 1/2 inch line, and 4 to 5 times the amount of water a 1/4 inch line can carry. So if we have too small a fitting in a line, we restrict that flow to that small fitting. So the size of the plumbing is the gatekeeper for that water. So the smallest fitting we go through limits the flow rate we can put through it. And then there's poorly designed filtration. If filtration isn't right-sized for the application and the flow rate, you may have a specification that is counting on intermittent water use, where one device is going on or a couple of them are coming on at the same time, but not all. And if you have a very busy operation where all this equipment is being used at once, let's say in a morning rush at a coffee shop, you may be demanding more water through that filter that it can actually handle, causing premature fouling, or in some cases, pulling that dirt through that filter and causing chlorine breakthrough and taste or odor control breakthrough before what we need. Plus, now that filter becomes a restriction to flow rather than a smooth pathway if it's slightly undersized and not sized for peak flow rate. And then the other source of reduced pressure flow is filtration beyond its useful life. When it's so loaded with dirt that you can't physically push water through at that pressure any longer. So these are all important variables that we want to overcome in supplying water pressure and flow to our equipment, because that plumbing infrastructure is the lifeblood of that equipment. Without it, it will not get water, and we have to supply it with the right amount of water for it to function properly. So water pressure and fountain dispensers. The water supply to a fountain equipment must provide dynamic pressure, means pressure at flow of the water, not when the valve is shut off, but when it's open, of greater than 50 psi to maintain that even Brix ratio. A flow rate greater than 6.5 liters per minute for each carbonator, or 1.67 gallons per minute, because carbonators have pumps that are water cooled. And if we do not feed them the proper amount of water, those pumps will cavitate. And they tend to be carbon-veined pumps. And carbon veins will shatter if they are not constantly bathed in water, because they produce too much heat, and when they cavitate, too much vibration, which causes them to break. If you've ever been back of house at a restaurant and heard a carbonator that's starved for water, it creates quite a bit of ruckus, a very loud noise that can be heard front of house quite easily. Where the water supply pressure and flow rate is inadequate, a water booster must be installed to maintain that even pressure and flow for those applications, maximizing profitability and uptime and filter life. Water booster provides additional water storage that's under pressure to assist the carbonator or whatever application in pump in meeting the total demands of that system. How those are typically placed is we place the water booster between the inlet water supply and the filtration. And the reason why is, A, we want to boost the pressure to the filters so that they get maximum life out of those carbon filters rather than the low pressure trickling through and then feeding the water boost. Also, if the water boost system develops any taste or odor issues, the carbon filters will handle any of that taste and odor issue before being dispensed. And then you have the CO2 supply that'll feed the carbonator pump. You want to make sure we're getting that carbonator pump its proper flow rate so we don't damage it. And that's where the water boost before the filters comes into play, because if this was on the filters were on the low pressure side of the water boost, we would be subjected to the impact of that low water pressure on filtration, reducing the life of those filters. And then it's either fed through a cooling system to pre-chill the water so that it's carbonated and stays carbonated before it gets dispensed at the carbonated valve, or it may have a cooling system that's associated with a non-carbonated valve for like lemonades and iced teas dispensed at a beverage dispenser. Now, a water booster has several parts. You have the water inlet, the pump itself, which is the black head of the pump, and then you have the motor that drives that pump. And then you have the pressure switch, which controls when the water boost will turn on and off based on a pressure differential for the tank. You have the water outlet that connects to the distribution system prior to filtration. And then you have the accumulator tank, which is a bladder tank that acts as the storage device and pressure accumulator that drive that water out at the increased pressure and flow we require. Now, how a water boost works is that the water inlet comes here, the pump is there, motor turns on and off, and you have the pressure switch and the accumulator tank and water outlet. Now, you have a butyl rubber bladder that stores the water, and you have a tank that is filled with air that creates pressure on the bladder. So what happens when the water boost is in operation? The pressure switch controls the operation of the pump motor. So when the pressure switch turns the pump motor off at high pressure when this tank is filled with water, depending on the pressures we select, they're typically 60 or 90 psi, this will shut off at. Now, the pressure switch will turn the pump back on when it hits its low water pressure, which is typically 20 psi below the shutoff pressure. So if it's 90 psi, it's going to come back on at 70 psi to start filling this tank back up. If it's a 60 psi water boost system, it'll shut off at 60 and then turn back on at approximately 40 psi. Now, the accumulator is filled with air. The air exerts pressure against the bladder, pushing that water back out when the application asks for water. With no water flow from the system, the bladder inside the tank is filled with water. The pump pressure switch is operated at the high pressure system, shutting off the motor, and the pump motor is off. Now, when an application demands water, the water is forced from the bladder by air pressure in the accumulator, squeezing it back out, and then the pump pressure switches on at the low pressure setting, and the pump motor turns on, attempting to fill up this bladder or producing flow for the system. Now, when the application stops, when the beverage dispenser is done filling up a cup of soda and it shuts off its valve, the pump pressure switch is operated at the low pressure setting, so it's on. And what it's doing is it's filling the bladder with water, and it's starting to do so. This will take a little while for it to fill up. So what happens with no water from the system and the bladder inside the tank is filled with water and it reaches that maximum pressure of 60 or 90 psi, the pressure switch is operated at that high pressure setting and the motor turns off and the system's recharged, waiting for more demand. Now, water boost maintenance is important. The air pressure in the accumulator must be checked regularly at PM visits because that's the driving force to squeeze the water back out of the tank. And without it, there is no pressure in the system. And the air pressure in the accumulator must be checked when there's no water pressure in the system because we want to achieve a consistent pressure pushing that water out. And the accumulator tank is filled with air through a valve located at the end of the tank here underneath this cap. And it is a Schrader valve, just like a bike tire valve is in order to fill that bladder tank. You do not charge the accumulator with CO2 for two reasons. If a leak ever develops in the bladder, you may carbonate that water, and carbonated water is acidic and will react with brass or copper components in the system, corroding them. Also, if there's any moisture in that tank itself in contact with the CO2, it may create carbonic acid as well and cause corrosion to the stainless steel tank too.